Okay, so when we look at that, we could label it as hydrogen NMR, but one of your big tip-offs that you're looking at hydrogen is that it's 0 to 14. The one underneath it, if it's not hydrogen, should be carbon, and we know it's carbon because it goes 0 to 200-ish. Okay. We've got our IR ranges, which is not an exhaustive list, but it covers, I think, the majority of things that you would find. And then our mass spec, here are our big kind of bullet things on what you should be pulling out of mass spec. So right here on this slide summarizes pretty much everything we need when it comes to chapters 15 and 16. It's now just how do we apply that knowledge. Okay? There's that organization sheet again, which I think is useful, and I would highly recommend you use it. And then look at that. What do we have right away? We got a bunch of peaks. Yes, I accept that. Keep going. Okay, carbon hydrogen, SP3. We have an OH. Does anybody want to challenge that being an OH? Could be an NH. Why are you switching up your guesses on that? What about that as an OH makes you nervous? It's very, very sharp. The OH can change breadth from being broad to sharp depending on the hydrogen bonding environment it's in. Okay? If we get lots of external hydrogen bonding, we get a broad OH. Okay? If there's internal hydrogen bonding, that hydrogen is now locked into the structure. Because it's locked into the structure, we don't get varying energies of that bond, and we get a sharp peak. What else do you see?
Possible SP2.
Why do you see a possible SP2? Just north of 1500 right there?
No, maybe a little bit further out. I haven't got it too well yet. Carbon.
Okay, so there is something about there. It's kind of hard to see that, but that's 1600. That's 1700. So there's something darn close to that 1700. So it's probably a carbonyl. It's a little on the low end for that. Okay. And then we got these other peaks here, which could be a tip-off of some kind of carbon-carbon double bond aromatic. And then we get all of this, which is fingerprint region, which you can pretty much ignore unless you have to. There are a few cases where you will have to, okay, but it tends to be fairly rare. There's the structure. Does it match? Do we have the OH? Okay. Do we have a carbonyl? Okay. Do we have a carbon-carbon aromatic? Okay. Do we have carbon-hydrogen SP3s? What is something that stands out as you're like, wait, where's that? That carbon-hydrogen would be an SP2. That should show up greater than 3,000. This really does kind of suck and is a bit unfortunate, and I'm not sure I can pull it off on the screen, but we'll try it. If you're at home, what you can do is grab a sheet of paper, okay, and align the sheet of paper so it's flush against that bottom axis. The other side of that paper, drop to that 3,000 line. Anybody see that there's a little bit of a peak? Just greater than that. People are laughing at that. Like, that's crap. That's your CHSP2. Okay? Just barely greater than 3,000. This is why it is helpful to have something there to line that up. Okay? Was it obvious? No. If I asked you to label everything that's up there would be something I would look for. The CHSP2 would probably not be something I would look for because that's really hard to see. Okay? But if I gave you the structure and said identify everything in there, now I would expect you to dig out and see that. Make sense? Okay. Now what do you see? There's one quick answer that I deleted from the slide. What do you see? You're like, you deleted something? That's because I was that fast. That's a mass spec. You should be able to very quickly look at these and identify which spectra you're looking at. Okay? Because once you know which spectra you're looking at, you can now look at that rule set. Think back to your Gen Chem nomenclature. You had to identify what kind of bond it was before you started naming it. Make sure you apply the right rules to the right spectra. So in mass spec, what do? Peak furthest to the right. There's the peak furthest to the right. Actually, that is a peak. Okay? For those of you that are wondering, what the hell is that with tallest peak within 3 peaks? There's the peak furthest to the right. Where's the tallest peak within 3 peaks? That peak is our molecular weight peak. That is now the molar mass for our compound. Where is that compound found? 1, 2, 3, 4, 5. Where's that line? 3, 93. I now know the molar mass of that compound. There's a potential multiple choice question. What's the molar mass of this compound? 93. You think it's 92? No, that's 93. Okay. Next multiple choice question. Which atom is in there? Bromine, chlorine, nitrogen, oxygen? Nitrogen. We know it's nitrogen because 93 is odd. Okay. Next multiple choice question. How many carbons? You're like, dude, there's no way I could figure that out. Do we know there's nitrogen? Subtract the mass of nitrogen. What's the mass of nitrogen? 14. 79? That's why I don't like this unit. Thanks for laughing and rubbing it in. Bring a calculator. Use it. Okay? Of that 79, we have no evidence of bromine, no evidence of chlorine, no evidence of oxygen. Was oxygen even on the list? Then don't include it. No evidence of oxygen. This means, and we don't have anything to reference fluorine. Could it be iodine? Why is no iodine?
Iodine's like 126.
The mass of iodine is 126. Technically, I think it's 125 and 127. Don't quote me on that. I think I'm wrong. Okay? This is at 93. I don't have iodine. It's smaller than a single atom of iodine. Okay? Which means what's left over? Carbon and hydrogen. What's the mass of carbon? 12. I'm just going to pretend to do it this way. Look at that. Look at that awesome long division skills. 6.5. Okay? So how many carbons could I have? 6. C6. I now have some information about the structure. I could ask which of the following is a proper formula for this compound? So we could do C6, and we know we have a nitrogen, right? Would that have totaled up perfectly? No, we'd be missing some mass. What's that mass? Hydrogen. So 6 times 12 is
72.
79 minus 72? 7. There's a potential formula. Make sense? Okay, you're accounting for the mass of each of those particles. You notice at the bottom it doesn't say mass. It says mass/Z. What is Z? A letter of the alphabet. It's charge. Okay, it is a mass to charge ratio. We'll talk about what that means when we talk about mass spec. Okay, you don't need to know that because the charge is 1 for all of the questions you'll see. We now have a potential formula. Are there other potential formulas? Okay, we could bring in oxygen. Again, we have no evidence of oxygen, so we can't do that yet. Couldn't I have C5? Yeah, but that would mean 12 more mass units, right? Okay. Where do those 12 more mass units need to go? Hydrogen. Is that what you said? Yeah. Okay. C5H19N. Okay. How about okay, you're starting to shake your head no. Why? There's way too many hydrogens. There's a line where you've got so many positions that you can't fill. How do you figure out what that line is? One option is drawing it. You don't like that option. That unsaturation formula, if you know that unsaturation formula, that helps you out. Okay? CnH2n plus 2 is a fully saturated structure. Okay? This is not the formula, but this is a good approximation. What is our N for that last one? 4. So if I had C4, H, what was my maximum H? 10. N was 4. 2 times 4 is 8 plus 2, 10. Doesn't fit. Okay? So that is not a valid formula. Kind of makes sense? Okay? So if you have little bits of information about formulas, you can backtrack and start to cancel out some of these answers. Kind of, sort of?
The one above that isn't valid either, right?
Yeah, I don't think so either. I didn't want to do the math, but fine. C5H12 would be saturated. We're at H19. That isn't going to work either. C6H7, that would work. Fully saturated would be C6H18, 14. 7 is less than 14, that would be allowed. Okay? It wouldn't be fully saturated, but it is allowed. Make sense? Okay? That's what we're trying to pull from mass spec. That looks awful. That looks like full credit. Okay? What do we have now? Carbon. How do we know it's carbon? Because you erased it. Give me another answer. Look at that max number. We're up at 180. We're looking at a carbon NMR. What do we pull from the carbon NMR? How many? So each of those peaks represents, best answer there, the number of unique carbons. Because if there's symmetry in the molecule, they're going to have the same chemical shift. So it's not the number of carbons. So we would now go through and count 1, 2, 3, 4, 5, 6. You might wonder what's going on there. I like that. Put in a question mark. So 6, did I not count right? It should be 6 plus a question mark, with that question mark being that shoulder that made it difficult to see. Okay. What else does it tell you? You're like, nothing else. That's not bad. That's actually pretty good. Okay. That's how fast your carbon NMR should be. You should be able to do better. This is alkanes. These are probably all, with the number of them, I would push towards aromatic, okay, instead of saying just alkene.
Even up to 160?
Even up to 160, it gets a little bit close. That 160 starts to become a little bit questionable because it could be a carbonyl that's been pushed down, okay, but you're probably looking at that aromatic alkene, okay? Does it have to be 100% correct? No. What you're trying to do is get evidence that you can use and compile with other pieces. Okay? What would other pieces be if this was your only thing given? So first off, it won't be your only thing given. What else would be given? The other spectra. Okay, good answer. I like that. No, I'm not giving you other spectra. What else is given? Dang, I don't know what else. What else could possibly be given? What other information is given to help you solve what this could be? The answers. It would be in a multiple choice question. Look at your multiple choice answers and see which one matches 6 unique carbons with one being alkane type. Use your answer choices to help you whittle through things. Okay. What are we looking at now? HNMR. Why? 0 to 5, we're looking at lower numbers. Does this look messier than our last ones? Yes, that's because it's a lot more complicated. There's a lot more information stashed within it. You're still going to be running the same bulk ideas. Okay? How many, and this is where it's going to change my wording here, how many signals do you see? We're going 1, 2, 3, 4, 5, 6, 4. One, 2, 3, 4. That's why I said signals, not peaks. There are 4 signals, which means there are 4 unique hydrogens. Okay? Each of those hydrogens has their own chemical environment. So we could now draw conclusions about where they showed up on this axis, just like we did with our carbon NMR, to get some information about their types of chemistries. Okay? In that 2 and under range, those tend to be alkanes. This range, a giant freaking question mark. That doesn't mean there's not information there. That means if you analyze it, it's like analyzing the fingerprint region. You will find whatever you want, which is generally the wrong answer. Okay? So it's not ignore that, but don't analyze it based off the chemical shift alone.
Is it wrong to assume that could be the nitrogen
What nitrogen?
from the mass spec?
Did I say this HNMR belonged to the same compound that the mass spec came from? Don't start making assumptions. Okay? And I would argue, at least at first when you go through and do these things, don't start taking evidence from one spectrum and combining it with evidence from the second spectrum at first blush. Go through and evaluate each of those 4 pieces independently. Because while the big picture is to be able to do all of it all together so you get to one final structure, you don't want that to be the case, because that would suck for an exam. You want to be able to get credit for the small steps you've made along the way. Okay? That's going to be your multiple choice questions. That's why you should segregate and compartmentalize the individual spectra first. Okay? Once you've fully analyzed them, then you can start crossbreeding. Make sense? How are we doing? Little? Yeah? Okay. It is a lot. If you don't feel overwhelmed, it's probably because you haven't been doing the work. Right? Or you've done way too much work. So, all the way back to chapter 5, we've got our asymmetries. So finding stereocenters was dealing with our asymmetries. I don't know why this slide was here, except perhaps to maybe just remind you. Our big tip-off that we're looking for a chiral molecule is that we find a chiral carbon. How do we know we have a chiral carbon? 4 distinguishable groups. And I liked Bev's choice of words here. It was 4 unique. You mean we could use the exact same wording we use in spectroscopy? Yes. Okay. So if you can find those 4 unique things, that's a tip-off you have a chiral atom. Okay. Just like we end up doing for spectroscopy. Do we identify those unique groups? Okay. You can look for planes of symmetry, as we've talked about in class, and I've talked about with a couple people in here. Finding a mirror plane is very difficult. Some people see them right off the bat, some don't. Okay? So I don't recommend using planes of symmetry to find a chirality or a chirality. Okay? What I do recommend finding, because we did that, would be actually looking at a flow chart to come up with those relationships. These relationships will show up on the next exam. They will show up on the final. Okay? And identifying those relationships, sorry, I just heard what you said. And identifying, it gives me anxiety too. Damn. What happened is I changed the aspect ratio for the slide and didn't get back to fix the freaking image. Okay? So go back and look at the Unit 1 slides where they're actually organized appropriately. Okay? We looked at the relationships for these, right? Fairly confident? All right, so let's push it a little bit further. What happens if we have multiple stereocenters? Okay, so here we've got a compound with two stereocenters. How do you know there's two stereocenters? Isn't there a mirror plane? Because I told you, it's not a bad answer. What is the hybridization of these carbons? SP3, which means when we draw that structure, we're allowed two solids, one wedge, one dash. Is that how it's drawn? No. So let's fix it. Let's say wedge and wedge. Right? Now there's a mirror plane. Did I have to call them both wedge? Is there still a mirror plane? No. Okay. So this ends up being a tricky thing. So how can we look at this and identify that we have stereocenters? Chlorine versus carbon versus hydrogen. Chlorine versus hydrogen versus carbon. Hey, that's three unique things. How are these two carbons different from each other? We go out one further atom. That one's connected to a chlorine. The other one's connected to hydrogen. Is there a difference? Yes. Which means that center carbon, that red dot there, is a chiral atom. You could go through and you'd find it over there too. Okay? Which means those chlorines should be specified as wedged or dashed. Okay? We should add that. Well, how many possible stereoisomers are there for that compound? And we're done a lot. No, it's 3. Okay, couple of cheats. First cheat, total possible stereoisomers, 2 to the n. What is n? A letter after m. Thank you. It's the number of chiral atoms. How many chiral atoms were in that structure? 2. What is 2 to the second? 4. 4, last time I checked, was not 3. There's an internal mirror plane. Possibility, which means I can subtract 1. So there are 3 possible stereoisomers. Okay, how else could I solve that? So using the quadratic formula? No. That would kind of suck. I already have enough problems with my times 12 tables. Times 12 tables? Yeah, I agree. How else would we figure out how many possible ways there were to arrange those chlorines? Draw it out. When in doubt, draw it out. Right? I don't know who said it first, if it was Laura or me. Ask Laura. I think it was actually, I started yelling at students, and I think the abuse reflected back to Laura. Right? So let's look at that red carbon. Could the chlorine be wedged? Yes. So let's make it wedged. What else could it be? It could be dashed. Okay, but that blue carbon has a chlorine as well. Okay, so that chlorine could be wedged. At this point, I'm only looking at the red carbons, which means in this bottom structure, how am I going to draw the chlorine? The blue one. I'm going to keep it wedged. But what could the blue chlorine be? Could also be dashed. When we look across, we'll keep that wedged, and we'll keep this one dashed. I've now drawn all possible permutations. How many did I draw? 4, right? So there we go. 2 to the n was 4, but we said the answer was 3. Why was it 3? These two are identical, which means that last one doesn't count as a possible stereoisomer because it's a repeat of something I've already drawn, which means 3 possibles. Is anybody looking at this being like, but Mike, come on, look at the other diagonal? What is their relationship? Those are enantiomers. Okay. On deciding enantiomers, take a look at your chiral atoms. Okay. If it's a mirror, everything swaps. Okay. My pinky on my right hand is on the right. Is it on my right side? Well, it's my right side, but it's your left, right? My thumb is. What happens when we look at the mirror image? My left hand. They both exchange positions. So when we're looking across, what happened to the red atom? It was dashed and became wedged. It reflected across the mirror. Where's the mirror that we're referencing here? It's the plane of the paper was the mirror we were looking at for that reflection across. If we look at the chlorine, it was wedged and it became dashed, reflected across. Okay? So those two are enantiomers. Relationship with the last one? Those are now diastereomers. Stereomers. Also known as disastomers if you want to cause real organic chemists heart attacks. I'm not a real organic chemist, sorry. Doesn't affect me. Okay? And we now have all of those relationships that could come out. Where this becomes pseudo-relevant is when we're looking at a molecule that we're trying to make. We want to decide how many possible things could be made. Why? Well, if I only want one of them, how much of a challenge is it going to be to make? If I look at all the possibilities, I could see that there's 1,000 different possibilities. To make just one, that's going to be difficult. Right? So let's take a look at another example. Whatever that name is a drug. How many possible stereoisomers are there of that? So for those people starting to draw this out, yes, you can try and draw this out. That becomes a challenge, right? It'd be nice if we, say, had a formula. Even with that formula, you laugh. You're like, but then I have to know the stereocenters. You had to know the stereocenters anyway. Where are the stereocenters in your molecule? The carbon with the what? The double oxygen, that carbon? That is not a stereocenter. To be a stereocenter, you have to have 4 distinguishable groups. There are currently 4 bonds to that carbon, so that's good. Those 2 bonds are not distinguishable. They're going to the exact same place. That is not a chiral atom. Your chiral atom will need to be SP3 hybridized. The carbon to the right of it. Your right? I guess it doesn't matter. That one? Why no? The 2 chlorines are identical. We can't tell a difference between them, which means we only get 3 distinguishable groups. Is this a trick question? Was there only one? The red and the orange position are chiral atoms. Look, but there's only 3 things bound to it. Except for those implied hydrogens. Remember how I said implied hydrogens are a pain? This is why you have to watch out for them. Okay. So now how many stereoisomers do we get? How many stereocenters do we have? How many stereocenters? 2, so n equals 2. Stereoisomers is now 2 to the 2, which equals 4. Do you see a mirror plane in that molecule? No. So that's nice. When it becomes a big complex drug, we typically don't have mirror planes. So if we're trying to make that, okay, and to make one of those stereoisomers, there's 3 other possibilities that could have come out in our reactions. we need to choose our reactions carefully so that I limit those other products. Okay, there was a hand or a question? Was it no? Okay, I can imagine things, that's fine. Maybe it's the chloramphenical's fault. I honestly don't know what it does. So, identify if the molecule can be chiral by marking all stereocenters and determine the possible stereoisomers. So take an attempt. See what you come up with. If you got questions? For the first one, right, we've got a carbon that is SP3 hybridized, so that stands out. So we have the possibility for a chiral atom. That one's extra nice because we have the hydrogen not implied. So if we go through carbon, hydrogen, carbon, carbon, I see 3 carbons. How are those different? One's SP2. This carbon is SP2. The other 2 were SP3. Right? So that makes it different, but the other 2 were still SP3. So how do you tell the difference? This one goes out to a carbon. This one would go out to hydrogen. Is there a difference? Yes, which means they're different, which means that is a chiral atom. There's one chiral atom in that structure, no more, no less, which means our total possible stereoisomers would be 2 to the 1 or 2. We move to the next one. We're like, aha, I'm catching a pattern. SP3 atoms, wedges and dashes, tend to be giant red flags. Yes, they are red flags that you should very cautiously evaluate. There's our hydrogen, so yes, chlorine, hydrogen, but now we've got carbon versus carbon. They're both SP3 hybridized, so I don't see a difference there. They're both connected to 2 hydrogens, so I don't see a difference there. What do? Move to the next atom. What's the next atom? A carbon. Both SP3 hybridized. How many hydrogens? 2. Don't see a difference. What do? I continue on, and what do I continue on into? Itself, right? Because it's a ring, which means we've now checked for differences all the way around the ring. Did we find a difference? Nope, which means that was not a chiral atom. What is 2 to the 0? Sometimes I guess it depends on the definition, but it's 1. You get 1 structure out of that one. Technically, we don't really get any stereoisomers. There's just only 1 structure. Okay, there's nothing to compare it to. So wedges and dashes are a good first place to look. If you see a wedge or a dash, you might be like, yes, there's a chiral atom. Critically evaluate and make sure that you don't end up overlapping. Okay, and the last one, we went through and looked, and we see right away, hopefully the 2 that were identified. Then we say 2 to the 2 gets us 4. Okay, so we could see those. Are we have any questions about those? Or are you guys good on those? Good on those. Is there another one?
Yes.
Yeah, where's that other one? That carbon does not immediately look like a chiral atom because we'd go CH2, CH2, right?
That's CH2.
You go 1 atom further away and you're now CH2 versus CH. There's your difference, which makes those parent CH2s different, which means you have 4 distinguishable groups, which means that is a chiral atom. We have 3 stereocenters. It's not 2 to the 2, it is 2 to the 3rd, and we get 8 possible structures. If you're really excited about drawing these, draw all 8 and have fun with it. I'm not, so I'm not going to do that. Okay? But you should be able to come up with a pattern to be able to draw all of those. We walked through that pattern, okay, with that previous slide, which I'm going to go back to really quickly because for whatever reason it didn't trigger when it was actually up there. When we're looking at multiple stereocenters, if you have only one, you can only have enantiomers. If you have more than 1 chiral atom, now diastereomers and meso compounds are possible. Okay? You have to have more than 1 chiral atom to have diastereomers be a relationship or meso be a relationship. Okay? So that can be something to help you go through and do it. Again, arguably, I would recommend that you go back to that slide that causes all of us issues because I formatted it, didn't fix the formatting, but we'll work on that. Okay? Nomenclature. If we go through and take a look at these two structures, they are mirror images of each other. Okay? This version of it, we have a wedge, so the nitrogen's aimed at us. So this whole structure is now coming out of the plane towards you. That molecule is an anti-nausea drug, so you don't throw up. Cool. If we look at the other one, the mirror image of it, that now flips it, and that molecule becomes a teratogen, which is a fancy way of saying birth defects. Lots of birth defects. Okay? So if we were to make this drug, we might be like, well, there's only one chiral atom. That means there's only two possible stereoisomers. That other one I'm not going to worry about, so let's just give everybody the mixture. Half of the drug does what it's supposed to. The other half of the drug causes massive problems. That was thalidomide. That's why this whole subject became important. Okay? That also means that we need a way to be able to name these things differently. Okay? The connectivity within those structures are exactly the same. Our nomenclature, sort of officially up to this point, hasn't addressed how we could differentiate that naming. That differentiation is R and S. It's the same rules that we would use for E and Z. We shouldn't be calling it cis and trans. On Z same side, or E. Right? It's those same rules, and those are known as the Kahn-Ingold Prelog rules. Why do we need rules for this? Okay, well, it's all about directionality. Okay? Which way is my hand turning? Counterclockwise. Why did I turn? Which way is my hand turning? Clockwise. Wait, did I change the direction of my hand? No. By looking at the molecule from a different direction, it changes your perspective on it, and it changes how you would interpret it. Which means, when we look at these individual molecules, we have to very specifically look at them from a very particular direction. If you look at it from the wrong direction, you get the wrong name. Okay? There are all sorts of cheats that I've seen online for how to switch back and forth if you aren't looking at it from the perfect perspective. Those cheats, in my opinion, are successful 50% of the time. People are like, oh, that's great. That's 50%. That's better than nothing. There's literally two options, dude. 50% means you have no clue what you're doing. Okay? So that's why I don't trust those other methods and will always move the molecule into the correct formation. Okay? That correct formation is this big list of rules. First, you need to know if your atom's chiral, so identify it. Then assign priorities to each substituent. This one gets tricky because it is atomic mass. All too often, students will go through and label things because, well, that one has a really long carbon chain, so that has a higher mass, so that must be a higher priority. Does it have a higher atomic mass? You have to look at each atom and evaluate where your difference appears. So it has nothing to do with the size of the group. It has to do with the mass of the atom connected. Okay? If it has a higher atomic mass, give it a higher priority. Well, what if you can't tell a difference? You move to the next atom, just kind of what we've done. What if you still can't tell a difference? You continue to move to the next atom, okay? As we've been doing all the way through to assign or determine that chiral atom. Okay? There is one potential weird issue that can come up. If you have multiple bonds, okay, we need a new system to label this. That system is that we have to treat each pi bond as a new sigma bond. Okay? In the video, I referenced it as a phantom bond. So we end up adding phantom atoms to look at those connectivities. Once all of our groups have the priorities assigned, we need to change our orientation on the molecule so that the lowest priority is aimed away from you. So it has to be dashed. Okay? Once you're in that configuration, look at the numbering that you've put on for the other groups. If it goes 1, 2, 3 in a clockwise fashion, it's R. If it goes 1, 2, 3 in a counterclockwise fashion, it is S. That's it. Ta-da! Yay! Like that. That's really it. Now it's just that practice of dealing with it. Right? One of the things that I have noticed that becomes problematic, which is with how students will sometimes draw this. Okay? What I'm trying to draw is this structure up here. When they go through and do that, right, you see 1, 2, 3. Which direction is that? That looks like counterclockwise. But what was the assignment? R. But that's not clockwise. That's because that drawing sucks. That drawing does not accurately reflect the three-dimensional model. If we go all the way back to Unit 1, what did I say when we drew out that structure? The wedge and the dash need to be next to each other, making a V. They are not on opposite sides. That does not accurately reflect the model. When we're assigning R and S, we have to do it based off of an accurate representation. If your drawing is wrong, your answer is wrong. This is why it's important to draw things correctly. Kind of, sort of? That does kind of suck. I fully admit that. Okay, but that's what we have to do. That's why I told you to draw those things correctly. Okay? So, you want to look at some examples? To the person that said no, yes, I love it, because I don't want to look at examples either. But I heard a whole lot of other people say yes. Okay, so we're going to take a look at this lower left-hand corner. Okay. And not just because there's only one. And there's our one chiral atom. I now need to go through and look at my different positions. I've got a carbon. I've got a hydrogen. Please reconnect. I've got a carbon. Whoops. And another carbon, yeah? So we've got those 4 different colors. Are those all distinct? This was a copy over from before, so yes, they are distinct. So we now have to assign priorities. When we assign priorities, there's nothing saying that we have to go in any particular sequence. We can assign the lowest, we can assign the highest. Those are the easiest. Okay? In this case, which one's the easiest? The lowest is going to be the easiest. Okay? The CH3, I'm going to argue, is not going to be the easiest because you are comparing carbon to carbon to carbon. What is the difference in atomic mass for each of those carbons? Okay? That's not easy. Okay? The hydrogen, on the other hand, is the smallest, so it has to get a 4. Okay? Distinguishing red from orange from purple. To deal with this, we have to deal with their individual connectivities. If we take a look at the red one, what is it connected to? Hydrogen, hydrogen, hydrogen. What is the orange one connected to? Carbon, hydrogen, hydrogen. Is there a difference in priority already? Yes. If we compare, we're looking at hydrogen versus carbon. Okay, so the orange one has a higher priority associated with it than the red one. Okay. How about?
Is it because it has less hydrogens?
No, it's because carbon has a higher atomic mass than hydrogen. Okay. And for those people being, isn't that the same thing? No, I don't care if it's the same thing. I'm using the language that you need to be using. We have to look at that atomic mass. Okay. So let's bring the purple one in. What's connected to the purple one? One hydrogen. And now we run into the issue. It's really only connected to one other carbon. How do I make a fair comparison here? This is why we have the phantom carbon. Okay? That pi bond becomes a phantom carbon. Okay, so ta-da, there it is, phantom carbon. which means that carbon isn't connected to just a carbon and a hydrogen. It's connected to a carbon, a hydrogen, and a phantom carbon. What does that mean for us? That purple one is for sure, I do see your hand, give me a sec. That purple one is for sure higher in priority than red. So what does that mean? Red is 3. Okay? Because we already said orange was higher than red. Now, orange versus purple. They're both connected to carbon, right? They're both connected to hydrogen. Hydrogen versus carbon, the purple one wins, has a higher priority. The purple one becomes 1, the orange one becomes 2. Okay? Damn. 1 to 2 to 3, which was counterclockwise. Good for being able to jump to that next gun. Okay? That went in counterclockwise direction, which means S. But wait, did we orient the molecule appropriately? How does the molecule need to be oriented? Lowest priority needs to be aimed away. Where's the lowest priority aimed? Away. It's already on dash. It's literally in the formation that it needs to be to do the assignment. We don't have to do anything fancy with this. For those people, that's not a perfect Newman. It's not. And you can do a slight tweak to the structure if you want to get to the perfect Newman. You'll get the exact same answer. Okay, as long as your lowest priority is dashed and you've drawn the proper things there, you're good. Okay, kind of makes sense? Let's make this more difficult. How does this change my priorities? So now when we look at the orange one, what's it bonded to? Another carbon and a hydrogen and another carbon. Which means at this stage, by just adding a methyl group to that position, can I tell a difference in priority between orange and purple? No, so what do I have to do? I go to the next atom further away. The next atom further away is a carbon over here. The next atom further away over here for the orange one is going to be this carbon. Why am I going to go to that carbon instead of the CH3? The CH3 is bonded to 3 hydrogens. What's this carbon bonded to? A carbon. Which of those positions is higher priority? That's why we go to that carbon and not the CH3 carbon. Okay? So now we can go through and compare for that next position. That purple one, light purple, is that better? What is it bonded to? 1 hydrogen and carbon. What's the orange one bonded to? 2 hydrogens and a carbon. Can I make a fair comparison? Is there still a phantom pi bond? Yes. That phantom is still there, which means the top one still takes priority. Our purple one gets our highest priority still. 1, 2, 3, 4. So that phantom thing can pop up in 2 different places. What if we had a triple bond? That's 2 phantom carbons per carbon. What if I had a carbonyl? How many phantoms? 1 phantom to an oxygen. Okay? That's our basics for R and S. I would recommend you practice those. Unfortunately, we've got to be done.